Okay, so this week I'm going to do some more exercises in Excel this time. And this week we'll be looking at the binomial distribution, we'll be looking at the Poisson, and also the hypergeometric. All right, so first one is number 32. I'm just going to take some out of the book and just work them in Excel to show you how I would do them. So consider a binomial experiment with n equals 10 and p equals 0.1. Compute f of 0, f of 2, probability x less than or equal to 2, probability of x greater than or equal to 1, the expected value, the variance, and the standard deviation. So since we're doing this, this is going to be using the binomial distribution. So that's the Excel function we're going to use is just binom.dist. And within binom.dist, it tells us we are going to look for number underline s, trials, and probability underline s. And that's just going to be x for the number s, n is going to be a number of trials, and p is going to be our probability. So from our problem, we have n is 10, p is 0.1. So we have those two. So x is really the only one we have to worry about. And they give those to us in the problem. All right, so what I did was I just went ahead and went from x from 0 to 10. And looks like I deleted my own number there. And so then I used the binomial.dist. And what we have is A16, that's going to be our x. The B12 is going to be our n. B13 is going to be our probability. And then we want false. That's when we do this, it's going to be cumulative or not. And so if we type it in here, you can see if I start, it's either false or true. And we want false because we want the probability mass function. And so that's the one we want. So we hit enter. And so f of 0, well, that's just going to be the first one, f of 0. And what I did was, like I said, I typed in 0 through 10, and then I did that first one. And what I made sure to do was put the $sign on the B and the 12 and the B and the 13. And so then all I had to do was copy down. I just hit Control D, and it copied it down. And what that does is every time it moves down one, it moves up one on the A16, it goes to 17, and 18, 19, and it's just taking that number right beside it and using that as the X value to calculate the value here. So for f of 0, well, that's just this value. So I just said, well, it's equal to f of 0 here. The next one, well, that says, what is f of 2? Well, that's just this one, 0.19371. When I just said that's equal to B18, so I just said go to that cell and take that number. Now, probability of x less than or equal to 2. So that means we're going to actually have to add up all of them from 2 on down. And so what I did was I did a sum. And I did the sum from B16 to B18. And so that gave me the sum of all those three. And for probability of x greater than or equal to 1, well, greater than or equal to 1, it's going to be from this one all the way to the end. So I could take that sum, or you could take 1 minus the 0. And that's what I did. I took 1 minus the 0. And so that's going to be 1 minus the 0.348678. And that gives me 0.65132. All right, now expected value of x. Well, what is that going to be? Well, that's just going to be the B12 times the B13 because it's just going to be the n times p. And for the variance, it's just going to be the, excuse me, the expected value times 1 minus the probability of success. So 1 minus that, and that gives us a value of 0.9. And what is variance? Well, that's sigma squared. And what is standard deviation? That's sigma. So if we take the square root of the variance, we get our standard deviation. And so now I have answered all of the values it asked for this problem. All right, moving on to the next one. Military radar and missile detection systems are designed to warn a country of an enemy attack. A reliability question is whether a detection system will be able to identify an attack and issue a warning. Assume that a particular detection system has a 0.9 probability of detecting a missile attack. Use the binomial probability distribution to answer the following questions. A, what is the probability that a single detection system will detect an attack? If 2 detection systems are installed in the same area and operate independently, what is the probability that at least one of the systems will detect an attack? And if 3 systems are installed, what is the probability that one of those will detect the attack? And D, would you recommend that multiple detection systems be used, and explain? All right, so same kind of thing here. We're using the binomial distribution. The number of trials is going to be, that's going to kind of vary. One of them is going to be 2 if we have 2 systems. One of them is going to be 3 if we have 3 systems. And then the very first one is going to have 1 system. Well, the probability with 1 system is just going to be that probability here, 0.9. So answer to A is just going to be the 0.9 because 1 system, it tells us that probability is 0.9. But what if we move on to the 2 systems? Well, then we have the number of trials n is 2, probability is 0.9. And so again, what I did is I went ahead and did the whole table here. I went 0, 1, 2, and then I calculated each of those probabilities by using the binomial distribution again. And so it's going to be, you know, just plugging in the values we have, the 2, the 0.9, and the x is 0, 1, or 2. So that just kind of does that for all those. And what we want for this one, if 2 detection systems are installed in the same area, what is the probability that at least one of them? Well, that's going to be the sum of basically the first 2, or the last 2, I mean, sorry. Yeah, okay. So that's going to be pretty high because you're going to have 0.18 plus 0.81, that's going to be 0.99. Now, if we move to 3, we do the same thing, and if it detects at least one of them, so it's going to be this one, and this one added together, and when we do that, take that sum, that's 0.999. So as you can see, we went from 0.9 with 1, 0.99 with 2, and 0.999 with 3. So I would say multiple detection systems would be ideal because every time we do another system, we're getting closer and closer to 1. And so I would say that would be the best way to do this one. All right, number 40. A study conducted by the Pew Research Center showed that 75% of 18 to 34-year-olds living with their parents say they contribute to household expenses. Now, suppose that a random sample of 15 18 to 34-year-olds living with their parents is selected and asked if they contribute to their household expenses. Is the selection of the 18 to 34-year-olds living with their parents a binomial experiment? Explain. If the sample shows that none of the 15 of the 18 to 34-year-olds living with their parents contribute to the household expenses, would you question the results and why? And then what is the probability at least 15 of the, or at least 10 of the 15 18 to 34-year-olds living with their parents contribute to household expenses? All right, so this is still the binomial distribution. And so my answer is, well, yes, it is a binomial experiment, and the reason is it fulfills all the items. It's a random selection. P is the same for all trials. It's always the same. The trials are independent of each other, and there's 2 possible outcomes that either they do or they do not contribute to the expenses. Okay. So next thing, if the sample shows that none of the 15 18 to 34-year-olds living with their parents contribute, would you question? Well, I went ahead and did again the whole, you know, x from 0 to 15 and found all their f of x's. So f of 0 is basically 0, that's 0, that's 0, that's 0. So would I question it? I would not question it because basically this is 0. So if none of them do, that would be a good thing. So I said, yeah, f of 0 is 0. So yes, I would agree with it. I wouldn't question it. Now, what is the probability that at least 10 of the 15, 18 to 34-year-olds contribute? Well, that's just going to be a sum. And so it's just the sum of those. And so that's what I did there. I took the sum of the 0.16 all the way to the 0.013, and I got 0.8516. And so that was my probability, or my probability that at least 10 of them would. Okay. All right, so moving on. Now we're going to do the Poisson. All right, so in Excel, the Poisson is going to be the Poisson.dist. These are the 3 items it's going to ask for in the function, x, the mean, and cumulative. X is just going to be our x. The mean is going to be our expected value, or the mu. And cumulative is, again, we're going to want false because we want that probability mass function. All right. So with this one, mu is equal to 3, so that's what I have here. I just kind of rewrote it down here. And what I did is I decided I wanted to go ahead and just find f of 0, 1, 2, and 3, not even worrying about what the question was. And that way I could just kind of practice using the Poisson. And I think that's kind of a good idea for you to do as well. So the Poisson distribution is going to be Poisson.dist. And for f of 0, that's x, so that's going to be 0. And then our expected value is 3, so that's going to be 3, and then comma false. And so that's what that is. And so then if I move down, the next one, I'm going to have f of 1. Well, that just means x is 1. And then here, f of 2, so that means this x is going to be 2. And so those are my 3 values. All right, so what is the appropriate Poisson probability function? With mu equals 3, we just plug in mu equals 3 into the function, and that's what we get here. So f of x is going to be 3 to the x, e to the minus 3 over x factorial. And that's just because, again, the mu is equal to 3, so we just plug that in. Now f of 2, well, I did that already. That's 0.224, and so I just said it's same thing here. I just put it in again. F of 1, well, that's already been calculated too, and I just kind of plugged it in there. And the last one, p greater than or equal to 2. Well, I'm just going to take 1 minus the other 2, the well, and I guess I used these 2 here, but you could take minus, well, I better have to do these because I forgot the 0, greater than 2. So that one, so I want to add those 2 together, subtract that off of 1, and then that gives me this value here. All right, so moving on, another Poisson. According to the NOAA, the state of Colorado averages 18 tornadoes every June. And so it says, note, there are 30 days in June for those who don't know that. Now compute the mean number of tornadoes per day, compute the probability of no tornadoes during a day, compute the probability of exactly 1 tornado during a day, and compute the probability of more than 1 tornado during a day. All right. So first we have to compute the mean number of tornadoes per day. Well, that's just going to be our expected value. So that's just going to be our 18 divided by 30, which is going to be 0.6. Now the next one, compute the probability of no tornadoes. So here in this case, x is going to be 0. So we plug in 0 into our Poisson. We have our expected value of 0.6 we found in part A. And again, false, and we get 0.5488. And that's going to be our basically our f of 0. Or yeah, f of 0. Now what is it for exactly 1? Well, then we want the f of 1. And we just plug in x is 1, still have 0.6 for our expected value, false, and that's going to be what we have here. Now, what if we want greater than 1? Now notice it's more than 1, not greater than or equal to 1, it's more than 1. And so what we're going to do is we're going to take off the f of 0 and the f of 1, and then it's going to be everything greater than that. And so we take 1 minus those 2, and that leaves basically the probability that it's going to be more than 1 tornado during a day. So it's not too high. All right, so that's 50. Now 54. A recent survey showed that a majority of Americans plan on doing their holiday shopping online because they don't want to spend money on gas driving from store to store. Suppose we have a group of 10 shoppers. 7 prefer to do their holiday shopping online. 3 prefer to do their holiday shopping in stores. A random sample of 3 of these 10 shoppers is selected for a more in-depth study of how the economy has impacted their shopping behavior. What is the probability that exactly 2 prefer shopping online? And what is the probability that the majority, either 2 or 3, prefer shopping online? All right, so now we've moved in to a new function, and we're doing the hypergeometric now. All right, so in Excel, they use different labeling than they do in the book. And so our population is 10 total shoppers. Now here, R is going to be our number of elements in the population that we're calling a success. In Excel, it's M. And so in that case, it's going to be 7. So 7 prefer to do their shopping online because that's kind of what we were looking to see who does online. And so what I kind of decided to do was kind of split this up into how this works. So in a function in Excel, we're looking for X, which is the sample S, N, which is the number of sample, M, which is the population of the sample, and our population of S, and N is the capital N is the number in the population. And what does that mean kind of for us? Well, that X is the number of successes, N is the number of trials, M is the number of elements in a population labeled as success. Again, it's our R. And then the last one is the number of elements in a population. And so that's kind of how you kind of have to go from the function in Excel to what we know in a book, and then try to get all the information from here down into here. Okay. So for part A, what is the probability that exactly 2 prefer shopping online? Well, that's 2 successes. So that's going to be 2. Number of trials, well, we pulled 3, sample of 3. So that's 3. Number of elements labeled as success, that was 7. And 10 is in our population. All right, so for the hypergeometric, what we're going to do is we want to find, in this case, f of 2. And so it's going to be just like the others. We just plug in everything we know. So it's, in this case, it's hypgeom.dist. And we are looking for sample S. Well, we found that was 2. The samp is 3. And population S is 10, and then our number of population, or 7, and then number of population is 10, sorry. And then again, we want false. And so when we hit enter on that, we get 0.525, okay? And that's what we have over here. And again, I just kind of did it over here to kind of see what it was, and then I brought it over here. Well, what is the probability that the majority, either 2 or 3, prefer shopping online? Well, in this case, I actually have to do another calculation before I can find the answer to part B, because I have to find f of 3, either 2 or 3. And so here, instead of the first one being 2, it's going to be 3 for the number of successes. So we're going to need 3 successes, and then 3, 7, 10 again, and false. And so then B then is going to be the sum of those 2 values, the f of 2 and f of 3, and that gives us 0.816667. Okay, and so that's going to be the probability that either 2 or 3 prefer shopping online. So again, that's the hypergeometric and how we're going to use that using Excel functions. And then our last one is a little longer. The Troubled Asset Relief Program, passed by the U.S. Congress in October of 2008, provided $700 billion in assistance for the struggling U.S. economy. Over $200 billion was given to troubled financial institutions with the hope that there would be an increase in lending to help jumpstart the economy. But 3 months later, the Federal Reserve survey found that 2/3 of the banks that received TARP funds have tightened terms for business loans. Of the 10 banks that were the biggest recipients of TARP funds, only 3 had actually increased their lending during this period. So it kind of shows the ones that increased, the ones that decreased. And so for the purpose of this exercise, assume that you will randomly select 3 of these 10 banks for a study that will continue to monitor bank lending practices. Let X be a random variable indicating the number of banks in the study that had increased lending. Okay, so that's going to be the success as increased lending. And so we want to know, A, what is f of 0, what is f of 3, compute f of 1 and f of 2, and then show the probability distribution for the number of banks in the study that had increased lending, and what is the value of x, which value of x has the highest probability. Then D, what is the probability that the study will have at least 1 bank that has increased lending. And E, compute the expected value variance and standard deviation for the random sample. So again, this is hypergeometric. This case, n is 10, capital N is 10, R is 3, little n is 3. And that X is what we're looking for, the number of successes. So we have to do 0, 1, 2, and 3. And so that's kind of what those first ones are doing here. So f of 0, we just plug that in. And so we'll have 0, 3, 3, 10. And so that's what we have up here. And then again, we're still using the false. We're using hypergeometric distribution here. And so we get for f of 0, 0.291. Okay, so what does that mean to me? Well, this is the probability that no banks should be willing. That's the probability no banks increase their lending in the study. Can't read what I'm meaning here. All right, then the next one is asking what is f of 3? Well, if we plug in 3 instead of the 2, or 0 rather, first one was 0, we get 0.008. So this is the probability that all 3 banks will increase lending in the study. That's very low. And so, with no banks increasing their lending, that was, 0.3. This is 0.008. What about 1 bank? Well, we plug in 1 instead of the 0 or the 3, and we find it's 0.525. And if we do the f of 2, we get 0.175. And so kind of the thing is, if we look at all those, the 0.525 is the highest probability. So that means 1 bank will increase lending is the highest probability of those options. All right, what was the next one? What is the probability the study will have at least one bank that has increased? Well, that's going to be greater than or equal to 1. And so basically, we're just going to take 1 minus the 0 one, okay? And that's just the easiest way to do that one, because if you know the 0, you just take 1 minus that. That's going to be everything greater than that. Now, expected value. All right, so here we have to kind of remember what the values are. So it's going to be our n times our m and divided by our capital N. Okay, and so if we plug all those values in, we get 0.9. Now this one, we have to plug in more values, and again, these values are straight from our book as far as what all this is, but we end up with 0.49 for the variance, and the standard deviation, we just take the square root of that variance and we get 0.7. So hopefully all these will help you do the binomial distribution, the Poisson distribution, and the hypergeometric distributions.